All right, team, we're jumping into chapter 8 now. And I want to first apologize in advance. It is raining cats and dogs here, and it might be kind of loud on the phone. I'm not sure. So I hope the audio is good. Okay, so we are jumping into chapter 8 and leaving behind what we've learned in chapter 7 about continuous random variables, and more specifically, the normal distribution. So the normal distribution, by and large, is the most important distribution in all of probability and statistics. And one of the reasons is that we know so much about it. And if we can somehow determine that a particular scenario is governed by a normal distribution, then we can make a lot of deductions based on that. So quite often we're trying to somehow see if there's some way to manipulate the situation so that we're dealing with a normal distribution, or at least something that's approximately normal. And it turns out that when we are taking random samples of populations and calculating their means of those samples, we are actually within the purview of a normal distribution. So let me spell this out more specifically. So in chapter 8, section 1, we're talking about the distribution of the sample mean. So first, let me tell you what a sampling distribution is. Sampling distribution of a statistic, remember, a statistic is a numerical measure of a sample, and a statistic corresponds to a parameter of a population, right? So every parameter of a population has a corresponding statistic. So mu, the population mean, has the corresponding statistic x bar, which is the sample mean, or sigma, the population standard deviation, has a corresponding statistic, the sample standard deviation s. So we're going to be talking about the sample mean, and more specifically, we're going to talk about the distribution of the sample mean. Okay, so the sampling distribution of a statistic is a probability distribution for all possible values of that statistic computed from a population with some fixed sample size. Okay, so let me try to get you thinking the right way here. So I've drawn this very basic picture where I'm representing the population that we're interested in as this big box. Okay, and this contains all the population. The population has a mean mu and a standard deviation sigma. Okay, now we're not going to assume that we know how the population is distributed, meaning the population could be normally distributed, it could have a binomial distribution, it could have a uniform distribution, a chi-square distribution, a Poisson distribution. There's all types of distributions. We're not going to make any assumption about how the population is distributed. Okay, so all we know about this population is that it has a mean and a standard deviation, both of which can be computed. So we're going to reach into the box and we're going to take samples out of the box, all of which have the same sample size. So we're going to go into the box and we're going to take a handful out of the box of a size n, little lowercase n, and that constitutes our first sample. And we're going to compute the mean of that sample, and I'll call it x bar 1, the first sample mean. Okay, so we put that stuff back, and then we reach back into the box, take another sample of size lowercase n, and compute the mean for that sample, and we get another sample mean. This time I'll call it x bar 2. And we can continue this process for as long as we want. We can continue grabbing samples out of the population, all of the same fixed size, and computing the means of those samples. And so we'll have a set of means, right? A group of different means, but all drawn from the same population and all from samples of the same size. So that's the scenario. So as it turns out, if we plot the computed sample means for each sample that we've taken out of the population. If we plot them as a distribution, it turns out that more often than not, the distribution of those sample means will be normal, regardless of how the population is distributed. So we're taking samples all of the same size out of a population, computing the means of each one of those samples, and then plotting them. And we're seeing that the distribution of those sample means is roughly normal. Okay, so meaning I take random handfuls out of the population and compute the means, and I get a lot of means that fall within this hump here. And then I will get a couple samples whose means fall outside, that are really high or really low, but there's a small fraction of those compared to those that fall in the middle. So that's the scenario. When we talk about this sampling distribution, we're talking about the distribution of the means for the samples that we've computed that we're taking from some population. And this is how they're distributed. More often than not, they're going to be normal. There are some caveats and some criteria that we need to cover, but this is sort of where we're headed. Okay, so more definitions. So we're only interested in, for this particular section, X bar, the sample mean, and in particular, we're interested in the sampling distribution for X bar, and which I'm going to call X bar distribution. Okay, so the mean and standard deviation for this distribution, right? What are they? So X bar is a sample mean, but don't confuse that with the mean of the distribution and the standard deviation of the distribution. The X bar distribution is its own distribution with its own mean and its own standard deviation. So if we have samples of a fixed size, lowercase n, and they're all drawn from a population with a mean mu and a standard deviation sigma, then the X bar distribution has a mean mu sub X bar, which happens to be equal to the mean of this population. So the mean of the sampling distribution is the same as the mean of the population. That's pretty magical. The standard deviation of the sampling distribution, which I'm calling here sigma sub X bar, is equal to the standard deviation of the population divided by the square root of the sample size. So the standard deviation is directly, or I should say maybe indirectly, related to the size of the sample. And in fact, what we can see here immediately is that the sampling distribution standard deviation gets smaller and smaller and smaller as the sample size gets bigger and bigger and bigger. So that's one thing we can see, is that the amount of error that we have in our sampling distribution is scaled according to how big the sample is. And this makes intuitive sense. We kind of know that if we take small samples and compute the means of those small samples, that somehow there's more error in a smaller sample than there would be in a bigger sample. The larger the sample, the more it reflects the nature of the population. So bigger samples are better. Okay. So one last thing, we often call the sigma sub X bar the standard error of the sample mean. So it's just another terminology. Okay. So that's all the definitions. Now we're going to look at two particular cases. What happens when the population is already normally distributed, and what happens when the population is not normally distributed, or at least we just don't know how it's distributed? What does that mean about the X bar distribution? What does that mean about the distribution of the sample means? So if we know that the population is normally distributed, which I say here, the shape of the X bar distribution for a population that's normally distributed with a mean of mu and sigma, what happens to the sampling distribution? Well, if the population is normally distributed, then the X bar distribution, the sampling distribution for the sample mean, is also approximately normal. So it sort of inherits normalcy from the population distribution. Please note that I'm using a capital X to denote the random variable that is drawn from the population. So big X means population here. So let me say it one more time. If the population is normally distributed, then we can assume that the distribution of sample means is also normal. This is very useful. Okay, so let's look at an example. So here we're going to say that the population, big X, is normally distributed with a mean of 100 and a standard deviation of 15, or a variance of 15 squared. Okay. We want to find the probability that the sample mean is greater than 110, assuming that the sample size is 10. Okay, so the thought process here is, first, since X is normal with a mean of mu and a standard deviation sigma, then based on what I just said previously, we know that X bar is distributed normally with a mean of mu, the same mean as the population, and with a standard deviation of sigma over square root of n, or a variance of sigma over square root of n squared. So that's the first step, is since we know the population is normal, we also know the sampling distribution for the sample mean is also normal. So we have to make that logical connection. Once we know that X bar is normally distributed, then finding this probability is straightforward. Here we can use our normal CDF function in our calculator. So normal CDF with a lower bound of 110, an upper bound of E10, a mean of 100, and a standard deviation of 15 over the square root of 10. So this is all the information you have to put in your calculator to compute this probability. So I'll keep that list here so you can see it. So going over this again, to pull up the normal CDF function, you hit second, you hit vars, you go down to the second option that pulls up normal CDF, and then you have to put in the lower bound, the upper bound, the mean, and the standard deviation. Close parentheses. So I filled in all of this information into my normal CDF function, hit enter, and it spits out a probability, 0.0175 approximately, which we know means that it's about 1.75%. Okay, so knowing that the distribution of X bar is normal means I can use this normal CDF function to compute this probability. If I didn't know that X bar was normally distributed, then I couldn't use this function to compute the probability. So that's very important. We connect that idea from the beginning. They tell us the population is normal, therefore the sampling distribution is also normal. All right. So the next question that follows is, what if the population isn't normally distributed? Then what? How can we handle this situation? We know that if the population is normally distributed, then so is the X bar distribution. But what if it isn't? What if the population isn't normally distributed? Well, this is answered by what we call the central limit theorem. So the central limit theorem says this: regardless of the distribution of the population, X, as the sample size gets bigger and bigger and bigger, the distribution of our sample mean gets more and more normal. So, central limit theorem, no matter how the population is distributed, I don't care if it's uniform, normal, Poisson, binomial, there's so many different ways that a population can be distributed. I don't care how it's distributed, as long as the sample size is big enough, the sample mean distribution will be approximately normal. That's pretty awesome. It's also really profound. So no matter how the population is distributed, the sample mean distribution will always approach normalcy or normality, assuming that the sample size is large enough. So the next question is, how big is big enough? So how big does the sample size need to be in order for the X-bar distribution to be approximately normal? The answer is that given the fact that the population has either an unknown or not normal distribution, if the sample size is greater than or equal to 30, then we can comfortably say that the X-bar distribution is approximately normal, with the same mean as before and the same standard deviation as before. So all we need is a sample size that exceeds 30 or is equal to 30, and we can safely assume that the sample mean distribution is approximately normal. So let's look at an example. So we're going to say that our population has a mean of 30 and a standard deviation of 12.9. But we do not know how the population is distributed. It has an unknown distribution. Now, stop to consider this for a second. More often than not, this is the scenario we're in as researchers, as scientists. We don't have a good feel for how a population is distributed. Why? Because it's a population. We can't possibly, for a lot of populations, we can't actually get our hands wrapped around the population. We can't probe the population. We don't know really how the population behaves. So this is often where we're at. We can compute a mean or deduce some sort of mean, we can deduce some sort of standard deviation, but we don't know how it's ultimately distributed. So here's the question. Assuming we know that mean, assuming we know that standard deviation, if we take a random sample with a sample size of 35, and that sample yields a sample mean of 36.2, then is this mean that was computed for that particular sample unusual? Okay, so let's see what the likelihood is that we would get this sort of mean. So the way this works is X has some unknown distribution. I'm just going to put a D. It's distributed some sort of way, and it has a mean of 30 and a standard deviation of 12.9. Okay, now, because this is the logical part, because the sample size is 35, which is greater than or equal to 30, because that sample size is big enough, we can assume that the sample mean distribution is normally distributed with a mean of 30 and a standard deviation of 12.9 divided by the square root of 35. So that's the central limit theorem. The only way we can make this claim is thanks to the fact that the sample size exceeds 30. So that's your check. If that sample size is below 30, then you can't make this statement and you can't use the following math. You're actually sort of SOL. There's no way for you to make any sort of deductions if the sample size is too small in this case. But the sample size is just big enough. So we can assume that the sample mean is distributed normally, which means we can compute the probability that the sample mean exceeds 36.2. So we want to determine how unlikely a result 36.2 is. So what we're going to do is compute the probability that we would get a sample mean of 36.2 or larger. So I can really make this greater than or equal to, it doesn't matter. So we just want to see how unlikely it would be to get a sample mean that's larger than 36.2. Now, since the X bar is normally distributed, yet again, we can use our normal CDF function. The inputs are the mean of the lower bound of 36.2, an upper bound of something big enough, E10, a mean of 30, and a standard deviation of 12.9 divided by the square root of 35. So that's all the parameters you need to put into that normal CDF function to use it directly. So I'm going to pull it up again. Second vars brings up normal CDF. We give it the lower bound of 36.2. We give it the upper bound. And look, if you don't like doing the E thing, you really can just do like one. I think 1,000 is usually big enough. 10,000 is definitely big enough. I'm doing one with 10 zeros behind it, but this will give us a result that's close enough. 30 for the mean, and then 12.9 divided by the square root of 35 for the standard deviation. Hit enter, and we get a result of 0.00223. Okay. So the question is this an unusual mean? So we took a random sample from this population with an unknown distribution with a sample size of 35. We computed the mean of that random sample to be 36.2. We want to know, is that mean unusual? Well, if we look at the likelihood of getting a sample mean of 36.2 or larger, we see that the likelihood is less than 1%. So 0.223%, right? Remember the rule. If the probability is less than 5%, then we claim that to be unusual. If it exceeds 5%, then it falls within the realm of, at least is not unusual. It may still be kind of extreme, but it's not unusual. Okay, so putting it all together, we have a population with an unknown distribution with a known mean and a known standard deviation. We take a random sample of a size 35 from that population and compute its mean to be 36.2. So this is just one sample mean. Now we're interested, is this particular value within the sample mean distribution an unusual value to have calculated? So we calculate the probability of getting that value or something larger, and we find that it falls well within the small tail of the normal distribution. So it's way out to the right. The probability was less than 1%, which is definitely less than 5%, and therefore is unusual. Okay, so this is where we leave off with section 8.1. This is a really big and important concept and section, even though it doesn't seem like a whole lot computationally, because we're just using the normal CDF function really to do all the computations. It's really the concept that's important. You need to really get a sense of the difference between the population distribution and the sampling mean distribution, and exactly what that sampling mean distribution is, right? You need to have a firm understanding of that. The concepts here are more important than the computations. So please study this closely. All right.